Hello and welcome to this reality modeling special interest group. Today's topic is focused on the best practices for photo acquisition. I'm Sylvain Lotto, Senior Application Engineer at Bentley Systems, specialized in photogrammetry and ContextCapture, alongside Benoît Frédéric, Product Manager for the reality modeling products. Probably most of you have already experienced failures using ContextCapture, and what's more frustrating than waiting hours for results that ends up useless. Most of this issue could be avoided by a better data acquisition and a better comprehension of the photogrammetric processes. Having a consistent dataset will take you through the photo alignment seamlessly, and you will be able to start your reconstruction serenely. Today's focus is context capture and photo acquisition, photogrammetric principles and limitations, camera model and setup, capture requirements such as overlap, angles, etc., calculation of the ground sampling distance and the expected resolution of your 3D mesh, and some real case example to illustrate the capturing process. So let's dig into a little bit of theory first. This is important to understand the requirements and limitation of photogrammetry. Photogrammetry is based on pixel recognition in multiple photos. It is a three-step process. First, we have zero triangulation. The goal here is to find the relative poses of all the photos. To do so, ContextCapture scans each photos to detect point of interest. We call them key points, and try to find corresponding points in the other images. When key points are linked from one photo to another, it generates a tie point. From tie points and a structure from motion algorithm, we are able to align the photos together. The second step is the generation of 3D information from pairs or triplets of aligned photos. For each pair or triplets of photos selected, a 3D point cloud is generated. This relies on the capacity of ContextCapture to detect similar points in the pair triplets of photos. Last steps consist in meshing the 3D points generating in the previous step and apply texture from the original photos on the mesh. As you have noticed, the definition of the pixel is at the heart of the technology, hence the importance of a quality dataset. The pixel recognition from one photo to another can be altered in some cases and naturally leads to the limitations of photogrammetry. There are three main limitations that we will review here. First, moving objects, shiny, transparent, reflective surfaces, and poor texture or no texture surfaces. For moving objects, we will have from one photo to the other pixels that are not consistent from one photo to another and with the background of the photo. So those moving object will be automatically discarded from the reconstruct geometry, but can still lead to some artifacts in the texture. Then for shiny, transparent, reflective surfaces, the problem is that the pixels from one photo to another will not be described the same way. For shiny or reflective surfaces, depending on how the lights hit your object, you will get you can get really different RGB values for the same pixel from one photo to another. So this may lead to holes in your 3D model or even bumpy surfaces. And same for transparent, of course. For transparent surfaces, you will get the RGB value of the object that is behind the transparent surface, so it will not be reconstructed. Then for poor texture or no texture surfaces, Um, we have kind of the same problem because the software is not able um, to detect similar point from one photo to another if all the pixels look alike. So this will generate again holes or bumpy surfaces. Now let's dig into the camera model and setup. Photos can be acquired by a wide array of devices, from the common smartphone, DSLR camera, camera mounted on drones, to top-notch cameras for large-scale mapping. Regarding the camera model and setup, any standard camera can be used, as we see before, but the quality of the photo depends on of the acquisition device, the quality of its sensor and optics. For example, for the same amount of megapixel, a camera with a larger sensor will produce photos of better quality. We have a few recommendations for taking photos. And first would be to keep a constant focal length throughout the acquisition. You are allowed to change the focal length if it is to circumvent a limitation. You want detail, but you can get close to the scene. But at least don't change the focal length for each and every photos. Then adjust your lighting condition and camera settings to avoid blurry photos. This is quite obvious, but it's really important. A quality camera will be able to deal better with challenging light conditions, so getting a good camera model is always better. Then ban any digital zoom and geometric retouches on your photos, as this will break the camera calibration model and probably fail your processing. Then for image formats, we accept JPEG format, TIFFs, and a lot of RAW formats. But anyway, for ContextCapture, for the processing, will turn your TIFF or RAW photos into high quality JPEG anyway. So to save you some storage space and processing time, you can work with high quality JPEG from the beginning, unless you want to perform some radiometric adjustment before submitting the photos to ContextCapture. About the data requirement and best practices, we have three main rules that if you follow them, that will ensure you a good photo acquisition. First, each point that needs to be reconstructed must be seen in at least three photos. At least 60% overlap between two consecutive photos, and a 15-degree maximum angle difference between two consecutive photos. This is all to ensure that enough common points will be detected between photos and ensure the success of the process in ContextCapture. Also, try to keep useless information out of the frame. Focus on your area of interest and avoid sky. To achieve this, you might need to adjust your distance from the subject and/or your optics. Here we are trying to remove any useless pixels that might either slow down the process or mislead ContextCapture. Keep an homogeneous resolution, same distance from the object throughout the acquisition. To capture more details, zoom with your feet. It means that instead of using your zoom on your camera, just get closer to the object to get a higher resolution. And if you do so, add transition photos to ensure pixel recognition. Circle around the scene at different levels to reveal any masked areas. Remember that it is better to capture too many photos than too few, because you can always remove some photos from your datasets, but it will be harder to capture additional photos if you need to. To link different sides of a building or an object or a scene, be sure to respect the maximum 15-degree angle difference. Too often we see customers having issues with their dataset for this reason. Last example to date is a customer trying to capture a bridge. Both sides of the bridge were captured almost perfectly, but hardly enough photos were linking the two sides of the bridge. So at the end of the day, the AT was not working properly and the complete model was not uh, reconstructed. Reconstructing interiors using photogrammetry is a difficult task. The short distance from the subject and the numerous objects creating masks drastically increase the number of photos needed to reconstruct the scene properly. On top of this, interiors often comes along with walls and furniture with almost no textures, which makes it really difficult to pass the AT and often leads to holes in the 3D model. Anyway, we recommend to use a fisheye lens in this environment, a tiny environment, to be able to capture most of the scene in your frame and get a better chance of passing the AT and getting a good reconstruction. This short video now shows you an exhaustive drone acquisition over a single building. Drone has been set to capture obliques at different angles, but also nadir imagery. Nadir imagery are important, especially if you plan on producing autophotos. So this is just a small example showing how capture of a single building can be done. Now, before going on site and doing your photo acquisition, it is important to be able to know how to calculate the ground sampling distance and the expected precision of your 3D model. The ground sampling distance, which is the size of a pixel of your photos in the real world, depends on the camera model, the lens, and the distance from the scene. With the image on the right, uh, you are able to calculate the resolution of your photos, ground sampling distance. Here we call it R, with the formula written here. The expected precision will be about 2 times the photo resolution, meaning that if you have a ground sampling distance of 1 centimeter per pixel, you can expect a precision of 2 centimeter for your 3D model. The calculation of the GSD using this formula is accurate for surfaces that are perpendicular to the line of sight. Now let me demonstrate a small example of overlap calculation for a drone flight, nadir only. So, regular standard flight planning, you want a longitudinal overlap of 80% and the side overlap of 60%. Now let's say that your project image size on the ground is 85 by 63 meters. You can calculate the projected image size on the ground using the formula in the previous slide. Now, the distance between consecutive photos should then be 2.6 meters and the distance between two flight lines 34 meters to achieve the required overlap. Anyway, survey drones generally come with flight planning softwares that automatically take care of this calculation. Now, let's dig in some real case examples. Here's the first one called drone 2.5 dimension. which means we have nadir only photos. Can be used for stockpile calculation, for example. This is the case here. It's a customer in the south of France that use ContextCapture to do volume calculation on the query. So this one is quite interesting because though it's a simple, quite a simple data capture, we can see that there are some challenges because of the change in the distance from the scene, because the query is quite deep. So we can see here that the pilot ensure enough overlap between the different photos, but also set the altitude of the drone to follow the best the distance from the object to keep a constant resolution in the photos. Indeed, you have to get the difference between altitude of flight and distance from the ground. Now let's open the 3D model. So the whole scene was captured with a resolution of 2 to 3 centimeters for the photos, which is about a really good resolution for this kind of application for volume measurements. Now let's see what I call drone 3D mapping example. So in this case, we have data set that is data capture that is a bit more complicated with nadir photos and oblique photos. So it can take a few seconds to load. It's quite a large project. Okay, here we go. So on the 3D view here, so we can see that there are several different flights and patterns. We can see on the top native flight that has been done for context and having an overview of the whole sites, as well as some close-up oblique photos at different levels for the single building to have nice details on the facade, etc. For each building, we also have some nadir flights on to get a good overview of the top of the building. And we can see that there are transitional nadir photos to be able to link the top one and the bottom one to ensure that pixel will be recognized perfectly and that the AT works well. We can see here the transitional nadir flights. Now let's open this 3D model, resulting 3D model. Okay, it's popped up here. Okay. So here, if we zoom into a specific building, we can see more details on the facade. Model look nice and sharp. This is, by the way, Bentley campus in the US. But we can see that there are still some data that cannot be captured from the sky, and maybe adding ground photo would be a way to get a better model. So that's for the next case here, drone 3D plus ground photos. So for this specific project, we combined two acquisition, one from the drone and one from the ground, but still ensuring to capture the data so that both merge perfectly. So again, this project is quite big. So okay, here it is. So in the 3D view here, you can see first the nadir flight, again to get context of the scene, quite high altitude, and nadir flight at different level to get closer to the scene. You can also notice some oblique photos done with the drone, circling around a specific point of interest of the scene. And then all the photos taken from the ground um, along the track, rail track. So for linear scene like this, so the operators walked along the rail track and capture photos at each step. But it's also important to add circles like this from time to time to make the aerial triangulation more robust. Working with long linear project can lead to some drift in the aerial triangulation, so it's always important to add some circular patterns at some point. So now let's open the 3D model, resulting 3D model. Here we are. So thanks to the ground photos, we can get some really nice details of single assets and features along the track and from the track itself. And thanks to the drone photos, we have details on all the top parts, roof, and the context around the scene. So here we can see pretty sharp details on the small building here. Okay. Next case is ground photos only. In this case, we had to capture this bridge over the rail track again, but in this specific scenario, we were not allowed to use drone to capture the scene. And to get even more complicated, the train traffic was not interrupted, so we had to be really careful capturing the photos, and we didn't get much time to capture the photos on the track. So in this case, and to make it even more complicated, there are some construction work on top of the building, so we were limited in the areas from where we could take the photos. So here you can see the pattern that was used to get an exhaustive data set on top of the bridge. And then under the bridge, because we didn't get a lot of time to capture the photo, we used a fisheye lens to capture a lot of the scene in only a few photos, and be able to get out the rail track before the next train arrives. So here the resulting 3D model. So we can see on top of the bridge we have some really nice details thanks to the exhaustive photo acquisition and repetitive pattern from step to step. And under the bridge, the resolution might be a bit lower, but still we get a really good 3D model of the scene with only a few photos. Next case here is um, it's in ground photos for interior. So I actually took those photographs in the basement of my building, and it was a challenging one because the area was really narrow and the lighting conditions were really bad. So I managed to get it work well by using a fisheye lens to be able to circumvent the fact that the environment is really narrow. And I used a DSLR camera with a good ISO range to be able to work under low lighting condition. So I worked by taking a round of photos at every, let's say, 60 to 80 centimeters. So basically at each step. Um, and it is along the different corridors of the basement. So you can work like this for a straight corridors, but then when you arrived at a U-turn, not a U-turn, but at a corner, you need to increase the amount of photos and the photo orientation so that you link perfectly the different corridors. And here you have the final result. Let's make me try to do a first person view. So here I was quite lucky because the scene is really good for photogrammetry. So we have gravel on the ground, we have brick walls with a lot of texture. So it really helped the software working well, even in these poor conditions. And then we have some example for street mapping. So this one is using a multi-camera system, high-end. It's actually 26 DSLR camera mounted on a spherical support. So it's quite expensive device. So it has been used to capture a specific street in France, and photos have been acquired. Set of photos have been acquired each and every 1.5 meters. Um, to capture all the details with really good overlap. Um, yeah, in this case, you can reduce the number of camera needed by using wider lenses, but you will lose a little bit of resolution, of course. Here is a 3D model. So from the street level, you can see a lot of good details. Of course, you can combine aerial data to get the top of the buildings, etc. But then you can see some defects in the glass parts of the shops, etc. But still, it's quite good. You can see also problem of texture with pedestrians moving from one photo to another, etc. Now last would be street mapping case, but using a single camera. This is a small test I did also in the street in Paris. So the hard thing with street mapping is that you have to capture both the ground and also the facade of the building, and you have a lot of masks from cars, pedestrian, vegetation. So here I worked with a DSLR camera and a fisheye or wide angle lens, 15 millimeters, and work with circles, overlapping circles. By doing this, you ensure um, to have a robust data set and to capture most of the detail of your scene. And here's the resulting 3D model. So we have good details on the facade and on the ground, and the fisheye lens helps a lot capturing both facade and ground at the same time, so you reduce the number of photos needed. And finally, real case example on city mapping. So this is more for yeah, just showing you. It's a city of Marseille. It's a really large project, and data was acquired using a, multi-camera system using flight lines. But yeah, so here's the resulting 3D model. The resolution was about 5 centimeters per pixel. So that was it for the presentation. Here are some contacts and information with links to technical question support, Bentley communities where you have a lot of information for the reality modeling brand and all Bentley product. The acquisition guide that sum up all we discussed here, some context capture tutorials on your YouTube channel, and different Bentley events and Bentley product training. Thank you for attending today's meeting, and thank you for your attention. Have a good day. Goodbye.